Almost all observations of the universe come by collecting light in various wavelengths. This light can show variations in brightness, reveal structure in cosmic objects, and contain huge amounts of information in how its wavelengths are distributed across a spectrum. Researchers have captured these details for decades, even centuries, but often they are limited to just a brief snapshot of an object in space, a single still image. In recent years, scientists have been making more observations with a fourth component, time. Space isn't static, and recording data through a given duration, called time-domain astronomy, tracks how details of an object, like brightness, spectrum, location, and structure, change. An object can vary, it can move, or it can do both. There are three main classes of how an object can vary in time: periodic, quasi-periodic, and transient. Periodic change means there is a regular, fixed pattern to the change. Sunrise and sunset or a blinking pulsar are examples. Quasi-periodic means that there is a pattern, and the change or event happens again and again, but not as regularly, like hurricanes or flashes from hot material around black holes. Transient events are less predictable and often happen only once. Earthquakes and supernovas are transients. These are the hardest to observe because they can be brief and start unexpectedly. If telescopes aren't looking in the right place, they miss the beginning or even the entire event. NASA's upcoming Nancy Grace Roman Space Telescope will be specially equipped to be a groundbreaking tool for time-domain astronomy. It will observe from space, so it won't have daily time restrictions like ground-based telescopes, which can only observe at night. It will have image quality like Hubble, but with a field of view at least 100 times larger, so it will be able to observe large portions of the sky all at once. Roman is a survey mission, which means that in addition to a large singular field of view, Roman can repoint that view more efficiently during observation periods, tiling even larger areas of sky 1,000 times faster than Hubble. For one of these, called the Galactic Bulge Survey, Roman will aim its expansive view at the center of our galaxy and observe a 2-square-degree region in infrared wavelengths that cut through the obscuring dust to reveal millions of stars. During this survey, Roman will take a new image every 2 minutes for more than 62 days, and then repeat this 6 times over 5 years for a total of 400 days of coverage. Roman will be watching for planets transiting or eclipsing their host stars, and rare gravitational lensing events where gravity of foreground objects lenses the light of background stars, causing changes in brightness. These peaks can reveal new planetary systems, rogue planets untethered to a star, and even black holes that would otherwise be invisible. A single snapshot of the sky can't show these events. They require constant or very regular monitoring to reveal. Roman's main objective in this survey is simply finding new planets and black holes. Astronomers anticipate that Roman could discover over 1,000 microlensing and 100,000 transiting planets from this survey alone. Observatories like the James Webb Space Telescope can then follow up with a narrower, more targeted view and learn key details about the most interesting discoveries. Roman will also perform time-oriented surveys aimed at furthering our understanding of the universe's history and future. With its wide and steady gaze, the Nancy Grace Roman Space Telescope will be a key player in the future of time-domain astronomy.